So we keep talking about this thing, computational thinking. We're talking about bringing it into the classroom. We've talked about how it fits into the curriculum. But I'd like to spend a few minutes just talking about what computational thinking actually is, because unfortunately, computational thinking has a bit of a stigma associated with it, as much as those of us in the room don't want that to be the case. And it's interesting because as soon as you put the word compute in anything, people lock up. And at Lighthouse Labs, because one of the things we do is get adults to embrace technology, one of the things we found that I wanted to be able to pass on to you as people who are going to go back and be training other adults, one of the things we found is that the biggest blocker that adults have when it comes to embracing technology is imposter syndrome. That idea that you're not good enough, smart enough to figure it out, that idea that somebody's going to figure out you're a fraud, they're going to tell you you're not worthy, that fear, that fight or flight mechanism that kicks in when we get approached with something new, when we have to wrap our heads around a new concept. And those of us in this room, we're already advocates. We already love technology, we embrace it, we want to see it flourish. Earlier when Jeremy was, when we had hands raising, the introductions were going on, nobody raised their hand for I'm concerned about this or I'm afraid of embracing this, which was awesome. That's not going to be the case when you go back to your districts and go back to your schools. If we can address the imposter syndrome up front, then we have an opportunity to get the adoption that we want. Quick show of hands, anyone seen the Eminem movie 8 Mile? Okay, few people. So I'm going to advocate what I'm going to call the 8 Mile method. And if you remember from the movie, if you made it all the way through, cinematic masterpiece. But if you made it all the way through and you get to the rap battle at the end where he goes up against, the other champion guy, there was something really interesting written into the movie. What he does is he walks up, faces the guy, and says everything that the guy's going to say to tear him down. He says it first. He addresses the fact that he's a white guy. He addresses the fact that he's inexperienced, that he lives in a trailer, that he lives with his mom. All those things get addressed. And by him addressing them up front, he takes the opponent's opportunities completely away from him. The one thing that we have found is the most successful in all of our explorations of computational thinking is changing the way we talk about it. Because computational thinking absolutely is part of our everyday lives. I can guarantee you I would be willing to sign a paper that says that every single person in this room has been doing computational thinking since you got up this morning. In fact, pretty much since you were about 3. You've been doing computational thinking. You just haven't been labeling it as such. For the purposes of what I'm going to talk about today, we're going to break computational thinking down into 4 key concepts. We're going to talk about pattern recognition, decomposition, abstraction, and algorithms. And for those of you taking pictures, all of the slides will be made available online. They're beautiful slides. We can thank Andrew for that, wherever he is. Yeah, all the slides will be made available online. You'll be able to download them. These are the key concepts that formulate the problem-solving method that is computational thinking. And that's where I want to start as a baseline. Computational thinking is a problem-solving method. It does not have anything to do with technology. It does not have anything to do with coding. Coding is a way to demonstrate computational thinking. Rescuing a ping pong ball from behind a chair when your eyes are closed is also a way to demonstrate computational thinking. So, I want to get the jargon out of the way. Because when I say words like decomposition, when I say pattern recognition and abstraction and algorithms, that is where that imposter syndrome kicks in. That is where people lock up because these are hard words. These are the words that tend to make people dig in their heels and not want to adopt because they are abstract concepts that we have to stop and understand. So what I want to do is I want to go through these 4 concepts, and the same way that Wendy spent some time earlier equating the curricular concepts with what is being done in the classroom already, connecting applied skills to ADST, I just want to connect computational thinking to everyday life. So decomposition. Decomposition, if I had to define it, it's taking a big problem and it's breaking it down into small problems. This is something we do every single day. So I've got a couple of examples up here. Recipe, making shepherd's pie. I love shepherd's pie, clearly. But when you're making shepherd's pie, there are multiple steps. You've got to make mashed potatoes. You've got to make the meat filling. You've got to be able to get the 2 of them combined in one pan. That's got to get baked, brushed with butter, all the good things that go into making shepherd's pie. Knowing that recipe and how to do all those steps in order to get to a successful result is decomposition. Most adults, we love to-do lists. It would be great because I think I have a to-do list of all the to-do lists I need to write. The scenario I've got here is you can't go to the dinner party until you pick up the dress from the dry cleaners. You can't pick up the dress until you picked up the car from the mechanic. You can't pick up the car from the mechanic until you've actually dropped it off there. This is a to-do list. There is a sequence of steps that you have to go through. We've decomposed the ultimate problem down into the series of steps necessary to accomplish it. And my favorite one is Carnegie Hall, the old joke that's been around for 100 plus years. How do you get to Carnegie Hall? Practice, man, practice. So if you want to get to Carnegie Hall, you're not ending up on stage by accident. You're starting off by picking some way that you perform, whether it's dance, whether it's music, maybe it's opera. You're practicing, you're picking a piece, you're rehearsing it, and then you're practicing. Anybody heard of the comedian Demetri Martin? Really, really funny guy. He has this great bit where he talks about his life goal is to live just around the corner from Carnegie Hall. That way, anytime somebody asks him directions to his house, he can say, practice, man, practice, and take the next left. I'm borrowing the joke, full credit. So the second term I want to talk about is an abstract one. It is abstraction. And abstraction is how we take a broad concept and we can represent it with a simpler idea. And this is something we do as adults every day. Some of us would argue that this is how we get through the day sometimes. But we look at behavior models as a great example of abstraction. So if I was to tell you to update your social media profile, earlier I told you to be social. I told you to tweet out about this event. I did not tell you, please take out your mobile device, please open up your laptop, please go to twitter.com, please sign in with your username and password, please click on the button to send a new tweet, please type in your thoughts, please use this hashtag, please use this username. I didn't tell you that. I said, hey, tweet about the event. If I tell you to update your profile, if I say, hey, can you drop the clothes off of the dry cleaners, I don't have to tell you how to get there. I don't have to tell you how to put the clothes in the car. I don't have to tell you to use the brake, the gas, check to see if you have gas. I don't have to tell you those things because we have already abstracted those concepts. And that abstraction is easy for us, and in fact, it's one of the keys to our effective communication is when the abstract concepts that I'm using, you're in tune with. And this one is actually pivotal, I believe, for when you are going back and training other teachers at your schools and your districts, because if we change the way we're talking about these things, then everybody is sharing the same abstract concepts. Pigeonholing, for example, if I told you that lunch was going to be Italian food, out there in the kitchen, we've had, so far we've had the stuffed croissants and we've had fruit and some pastries. But if I told you lunch was going to be Italian food, abstract concept, you have expectations. In your mind, you're picturing spaghetti, pizza, lasagna, carbs, a nap afterwards, maybe a little vino, but that's what's in our head when we have the abstract concept of Italian food. If we can share that same concept, then we're good. Last but not least, because I'm talking about the terminology, because I'm talking about changing the words we use, we have to think about the fact that there are words that we have in the English language that we have purposed for many, many different things. And I'm not just talking about, memes and text speak and things like that, but technologically speaking, if I say the word stack or tree, that means something. That's a command stack, that's a file tree. When an HTML page is rendered by a browser, it creates a tree of nodes. That's a technical concept. But if I was to go down to the corner, and grab a frantic Christmas shopper trying to grab a midday present here at Pacific Center, and say, nice tree, they would think I was talking about something wood with branches. The abstract concept ends up being the same. It's a question of how I'm purposing the term at that point. Queue, of course, we've all been in a queue, but most of us, if we were taking the bus or SkyTrain yesterday, we were in a queue. If you were waiting trying to get across the Knight Street Bridge yesterday, you were in a queue. So pattern recognition, this is the third big concept. This is something our brains love to do. Our brains love patterns. I keep getting caught, my eyes get caught by the pattern of the blue and white tiles here on the wall. We love patterns. We love to see them. We look at clouds and, oh, that one's a dinosaur. That one's, a unicorn riding a T-Rex driving a locomotive, whatever it may happen to be. Yeah, you'll have what I'm having, I know. But shape matching, square pegs don't go in round holes. And that's a statement that applies to the physical object of, blocks that your preschooler may be playing with. It also applies to how we might assign roles and responsibilities on a team. Rorschach tests, Christmas is coming up and the kids are going to be shaking boxes. I think this one looks like this box. Oh, I know that one's a PlayStation game. That one's something else. This is pattern recognition. We recognize these shapes and these sequences. And it's something we do every single day, but it's a key piece of computational thinking. Think back to your ping pong rescue that you did this morning. There were probably some repeated patterns in there, times when you had like one step and then one step, or one step and then two steps, or even if you had a step and a turn, and then later on you did that same step and that same turn. That's a pattern that keeps coming back. You can recognize that because our brains love to do it. Autocomplete is my favorite example of pattern recognition. So when you start typing a text message on your cell phone, most iPhones, Androids now, BlackBerry, will suggest what word should come next. Saw this great post making the rounds on Facebook about a week ago where it told you what you did was you type in the word Batman and then you hit the middle word 15 times and post in, on Facebook as a comment what the sentence is that your phone ended up building based on what it thought should come next in that sentence. And people had some really unique and interesting things that some of them, made you worry about what these people were typing every day. But, we've all gone to Google. We've started typing in the search box, how do I? And you get some interesting results based on what people are searching for. Google is trying to guess based on the most popular searches, based on your search history, based on trends at any given moment, what to fill in that box, what letter or what word should come next. And some of it may be, how do I get my car unstuck from the snow? Hopefully you're not getting the how do I get bloodstains out of my carpet? That would be a bad one. I hope that's not in your search history. But you have this predictive engine now that's based on patterns. Autocomplete is a technology that exists Because we behave in patterns. And of course, design patterns. We've all gotten the new remote control, when you've gotten, say, maybe you swapped from Shaw to Telus or whichever way you went to take advantage of the free TV or the iPad or whatever they happen to be giving away. And the technician comes in and installs everything and hands you something that looks like it's straight out of Darth Vader's bathroom. And you're like, oh, cool. And you very quickly figure out which is channel, which is power, which is volume, which one accidentally sets it to Spanish and you can never get it unset again. Those patterns, though, of what the controls look like, we know those. We know those patterns. If we get a new email app, we can very quickly figure out how to use it. And it's not because we're technical geniuses, though, of course, we are. Just ask us, we'll tell you. But it's not because we're technical geniuses. It's because we understand the pattern of the interface. That's a key piece for computational thinking because it's something you can do at any age, at any grade level. Pattern recognition is easy to do. Last but not least, I have to talk about the algorithms word because this is the word that I think has the most negative connotation on it. If I say algorithm, people automatically think math. And they're not wrong. Math formulas are algorithms. But there are other algorithms too. Fire drills. You've all got to deal with fire drills. In fact, whether you're an office employee, a teacher, a construction worker, you have to deal with fire drills. There is going to be an event that triggers that algorithm. And then there is a set of steps that must be done to produce a successful result, and they must be done in that order in order to keep you from being burned to death, which we don't want. That would be bad. So we do the fire drill. And an algorithm is a clear set of steps that will reproduce a successful result every time it's done. And if we talk about it that way, it stops being math. It stops being code. Google has the PageRank algorithm. Facebook has its news feed algorithm, which nobody can be satisfied with. We hear algorithm in that context all the time. But grandma's cookies are an algorithm. In my family, my partner, her mother, has the best pancakes I have ever eaten in my life. I have the recipe. She has written it down for me step by step. I have the algorithm for these pancakes. I cannot make them taste like hers, even if you pay me. I can't get it to work. Frustrates me, but the secret will be cracked at some point. But it's an algorithm. And every family has this one recipe that, Baba made when she was old and you remember it and it never tastes the same after that. But if you could get that algorithm right, that would be awesome. And the last one I have up here, quite frankly, is a plea for help, because if anybody has a good algorithm for parking in Kits, I would love to know what it is. Because here's my algorithm for parking in Kits. Drive to Kits, find where I'm going to go, drive around the block about 4 times, curse, drive home. That's my algorithm for parking in Kits. But the thing is, we have those tips and tricks. Like if you're going to a Canucks game, use this lot, it's cheap. And yeah, you have to walk 19 blocks, but it's totally worth it, I promise. The white spot down on Georgia near Stanley Park where, you can park for free and get away with it and then walk all the way across downtown. There are those tips and tricks that are out there. Those are algorithms that we use every day. It's just a matter of figuring out how do we get that result reproduced? How do we get the pattern that gets us to the successful result? How do we take the big problem, decompose it down into the small steps, figure out what the pattern of those steps is, figure out what the abstract concept is that we're trying to achieve, and then end up with a successful solution every single time. So it's not coding. And that's the other key piece. And yes, from a publicity point of view, from a PR point of view, it makes sense that many people are going to stand up and say, we're teaching coding in BC schools. And they're not wrong. But as Wendy pointed out earlier, and as I'm going to point out right now, and I will also point out again tomorrow, throughout the entire curriculum, we don't even start to bridge into text-based coding until grade 8. Visual programming will happen before that, but that's just starting to dip our toes in the water of coding. The actual text-based coding, HTML, CSS, JavaScript, we start to bridge into that grade 8 and grade 9 especially with ICT. Coding is an actually advanced way to demonstrate computational thinking principles. We've already shown here that a ping pong ball is just as good at demonstrating the computational thinking principles because you had to do all 4 of those concepts in order to successfully complete that activity. And there was a lot of negative press and a lot of eye rolling and sighing and shoulder heaving when it was publicized that there was going to be the ability to learn these concepts in schools without the need for computers. One of our mandates that was given to us by the ministry in developing this content was to make sure that there were unplugged options, to make sure that the concepts could be demonstrated without having to have an iPad in hand. Now, one argument for that is, of course, don't want to pay for iPads. Those are expensive. Lego Mindstorms, those are expensive. Chromebooks even, at $250 a pop, those are expensive. Yes, that argument can be made, but the truth of the matter is, and something we actually came to realize as we were developing this content, was that at the end of the day, there weren't extra concepts that had to be taught because these were things we were doing ever since we had gotten up in the morning. I'm going to give you my definition of programming because it has context here. Programming is a method of abstraction. If I, in my role as a web developer, am going to sit down and build an app for a client, I'm not coding. I'm breaking down a problem. I'm creating a solution and breaking it down into steps so simple that a computer can do it. At the end of the day, all of these laptops that we have in front of us, the mobile phones that we have in our pockets, if you have an Apple Watch or a Fitbit or whatever smart device strapped to your wrist, are dumb boxes. And that's something that's key for us to acknowledge because, again, it's changing the way we're talking about it. They're dumb boxes. What makes them valuable, what makes us spend the money on them that we do, is the fact that someone has come up with a solution to a problem that we have. Someone has come up with the solution to how do I get this box to turn on and show the Windows logo or show the Apple logo and get the user to a desktop? How do I play solitaire? How do I Tinder? How do I balance my checkbook? How do I play Angry Birds? All of the important things that are part of our everyday lives. Pokemon Go is a great example over the summer. Somebody came up with a solution and translated it into a language that the computer could understand. And that leads us into an interesting point. I got a great question during the break about the part of the curriculum that has to do with the evolution of programming languages. Rory, I think that was your question, yeah. So this great question of how, if we're not doing text-based coding until grade 8 or grade 9, how can we talk about the evolution of programming languages? And at first, I didn't have a good answer to that question. But I got to thinking about it, and I realized something that's kind of interesting. One of the things that I found very shocking when I first learned it was scientists have done studies. They put people in machines and shot them full of all kinds of rays, and unfortunately, they didn't come out with superpowers. But what the scientist ended up with was an understanding that in the human brain, the same part of our brain that would speak Spanish, that would order an espresso in Italian, that learns Hebrew or Farsi or American Sign Language or any other written or spoken communication language, is the same part of our brain that processes JavaScript or PHP or Ruby or Python or any other programming language. In fact, the reason we call them programming languages is because they are processed by our brain as languages. So the great way to talk about the evolution of programming languages is to understand that we use language to communicate a solution to a problem. That solution to the problem may be how to get a parking place in Kits. That solution may be how to make grandma's cookies, how to trade wheat for coin, all of the things that we would use communication for to accomplish that solution. We're doing the same thing with programming. We're doing the same thing whether we're doing visual programming, whether we're doing text-based coding. What we're doing is communicating to the dumb box. So if we understand the 4 principles that are built into computational thinking, and we can change the way we're talking about it so that it stops being this distant, unreachable, technical, mystery wonderland where wizards wave wands and apps appear, and we can talk about it as something we're doing every day. And even if we're talking about the strange characters that we have to type from time to time to actually program or code, we stop talking about it as if it's hard. We stop talking about it as if it's something that people can't adopt or something new that has to be learned. If you can learn grade 10 French, you can learn Ruby. If you can, learn how to say "Donde está la biblioteca" by watching, Community on TV, then you can learn how to make a game in JavaScript. That stops being the challenge. And then we get to defeat the imposter syndrome. We get to put a nail in that coffin of the resistance that is, I can't do this because it's hard. It's something new that I have to add in. One of our biggest goals over today and tomorrow is to give you tools that we have found useful in being able to have this conversation, in being able to use that 8-mile method and take the resistance out. Because you know your districts, you know your schools way better than we do. You know what the resistance is going to be. You've heard the complaints, the water cooler, man, if the water cooler could talk, right? The union would have fired it long ago. You know what the complaints are going to be. You know what the resistances are. You know where those pain points are. If we can change the way we're addressing it, we're going to be successful in getting it into people's minds and into people's practices. Like I said earlier, I don't have to convince you. You're the advocates, you're the champions, you're the evangelists. So it's just a matter of being able to have the right conversation about these concepts. We've already equated them to the curriculum. We already see where those lineups happen, where we can take projects that exist or that we would like to exist and quantify them as computational thinking is, and quantify them as the elements of the ADST. Well, now we can get to the point that we can talk about programming, and it stops being hard. It stops being something unreachable and new that has to be learned. All we have to do is figure out how to tell that the recipe for grandma's cookies at the end of the day. So, the other thing I want to talk about is if we're taking away these resistances, if we're taking away the complaints that people are going to have, we have to talk about what the end goal is. What do we expect out of all of this? And the expectation is not to create a legion, an entire generation of coders or programmers. It is to create a generation of computational thinkers. Very different goal. There's this phrase that I saw on a very opinionated blog post that was about Codergarten, the Codergarten generation. And when I read this, my skin literally wanted to crawl right off my body and run away. Because this is going to be feedback you're going to get. Well, we're just, forcing everyone to code. No, we're not. We're forcing people to realize that this is something they're doing every day. Computational thinking is a problem-solving method that allows us to address these big problems, the things that we want to decompose down, these abstract ideas. That's what we're creating, not rows and rows and rows of app developers.